Good morning, good afternoon, good evening from wherever you are in the world. Continuing with day 2 of this ARSET training, I'm your host, Asafa Nyamba, and today I'm joined by Professor Mike Quimberly, who will be your instructor for today's session, focusing on a case study on the use of remote sensing data to study climate-sensitive diseases with a focus on malaria in Ethiopia. From the last part of training that Professor Tatiana Loboda presented, she provided an overview of how remote sensing data can be applied to the study of climate-sensitive infectious diseases. A number of things we learned from that portion of the training is that remote sensing data can tell us about hazard, and that is identifying habitats and environmental conditions suitable for disease vectors. Also, to look at the exposure aspect of it, by identifying where humans might come in contact with disease vectors, and then vulnerability to be able to identify proxies for socioeconomic standing and access to care. Altogether, this allows us to assess disease risk. We also learned about different considerations of available parameters of variables, the coverage, resolution, data quality that may apply to each aspect of the risk. Finally, we also focused on satellite data pre-processing, which involves quality filtering, gap filling, regridding, and conversion to a common projection for an area of study. So today we are going to part 2 of the training, where we are going to examine a case study in the use of remote sensing to study climate-sensitive diseases, focusing on malaria in Ethiopia. As I had mentioned previously, homework will be posted on the training webpage at the end of this training session, and will be due 2 weeks from now. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due dates. And now for part 2. So for this part 2 training, we have quite a number of objectives that we would like to achieve. By the end of part 2, we want to be able to, one, identify the climatic and non-climatic factors that influence malaria life cycle, transmission, and the malaria global burden. 2, we want to be able to understand the specific requirements and rationale for malaria forecasting in Ethiopia. 3, we want to be able to explain the basic functionality of the epidemic prognosis, incorporating disease and environmental monitoring for integrated assessment of the EPIDEMIA modeling system and the satellite data used in its operation. 4, we want to list the steps taken by EPIDEMIA to access, pre-process, and harmonize remotely sensed climate data together with public health information. And lastly, we want to be able to identify common advantages and challenges of working with remotely sensed data for infectious disease forecasting as encountered in the EPIDEMIA case study. Now, just a reminder on how to ask questions. Please put your questions in the question box and we'll address them at the end of the webinar. Feel free to enter your questions as we go. We will try to get all the questions during the Q&A session after the webinar. The remainder of the questions will be answered in the Q&A document, which will be posted on the training website about a week after the training. Right now, I would like to introduce to you the instructor for the rest of part 2, Dr. Mike Quimberly, professor in the Department of Geography and Environmental Sustainability, and the acting director of the Data Institute for Social Challenges at the University of Oklahoma. Dr. Wimberly's research combines ecological models with satellite observations to address scientific questions and develop applications in the fields of public health and natural resource management, including wildfire and vegetation dynamics in temperate and tropical forest ecosystems. He also examines drivers and consequences of urbanization and agricultural expansion and the effects of land use and climate on vector-borne disease transmission. Michael, the floor is yours now.
Thank you, Asaf. I'm happy to be here, and I'm excited to present this case study on malaria early warning using satellite Earth observations in the Ethiopian highlands. And I'm going to start with some background on malaria and its transmission cycles. So malaria is a disease caused by Plasmodium parasites. It's transmitted between humans by mosquitoes in the genus Anopheles. One of the key factors with malaria is that the parasite is very complex. So it goes through a large variety of transformations, both in humans and in the mosquito. But the key factors are that we need humans and mosquitoes and the parasite all coming together in the same place in conducive environments to maintain the transmission cycle and keep transmitting the parasite from one person to another, causing disease along the way. So malaria is very much a global disease. If you go back hundreds of years, it was really all over the globe, everywhere from the tropics to temperate regions. But for a variety of reasons, we've seen shrinkage of the malaria map throughout the 20th century, such that now it is primarily a tropical disease, with a particularly strong focus in sub-Saharan Africa. And since 2000, during the 21st century, there's been huge global efforts aimed at reducing the malaria burden, and we've seen a lot of progress. So up through about 2015, there was steady declines in the global burden of malaria, largely due to coordinated global efforts to implement malaria interventions, again, particularly in sub-Saharan Africa. But what we've seen since 2015 is a concerning slowdown. So the rate of decline started to slow, and since about 2020, for a variety of reasons, we've actually seen slight increases in the global burden of malaria. So progress has been made, but currently we are in a slowdown, and there's concern about our capacity to maintain these gains and also to continue to reduce the global burden of malaria. Let's look specifically at Ethiopia. So like the rest of the world, the rest of Africa, this is a place where the substantial progress was made historically in bringing down the malaria burden, but particularly since 2020, there have been some huge reversals going on in Ethiopia. So malaria, again, while we're making progress, there's a strong potential for malaria to rebound when conditions change. So it's something that we're continually keeping an eye on, and where we need new tools in the toolkit to sustain and continue making progress in the battle against malaria. So why malaria forecasting? Let's talk a little bit more about Ethiopia. So this is Ethiopia is historically an area with what's called unstable transmission. So there's actually a relatively low and variable burden of malaria. But what that means is that humans generally do not develop acquired immunity to the disease. So when we do get outbreaks occurring under the appropriate conditions, they can actually be very large, and they have really high rates of morbidity and mortality, particularly in the adult population. And this is compared to other parts of Africa where malaria is endemic. We've got a variety of things happening. Ethiopia is a very mountainous country, so climate change is changing the climate, pushing climate suitable for malaria transmission up to higher elevations. There is drug and insecticide resistance. There's recently been introduction of urban malaria vectors from India. There have been challenges with sustaining interventions, challenges with civil conflict. And this has all contributed to the resurgences that I showed in the previous slide. And the idea behind outbreak prediction is that it can facilitate more rapid and targeted interventions that would reduce the public health impacts. So instead of reacting after an epidemic has peaked, there's the potential to implement responses before that peak and have a greater impact. One of the key connections between malaria transmission and satellite Earth observations is climate and weather factors, such as temperature, humidity, and precipitation. These all impact malaria transmission in a variety of ways. So if we look at temperature, mosquitoes are tiny ectotherms. Basically, they're the same temperature as the surrounding environment. So pretty much everything that happens inside a mosquito, reproduction, growth, mortality, biting, even the development and the transmission of the parasite, they're all highly sensitive to temperature. And we're also beginning to understand more about how atmospheric humidity mediates these temperature relationships. Looking at rainfall, that's a critical source of water for the larval habitats for mosquitoes. So they lay their eggs and the larval stages develop in temporary pools. This is sensitive to the water balance between rainfall and temperature and humidity, which impact evaporation. So there's a lot going on here. It's a complex chain of processes, and it takes some time for these environmental fluctuations to actually impact malaria incidence in humans. But that gives us an advantage, because if we can track temperature and humidity, rainfall, other environmental factors in near real time, and if we understand enough about these pathways to be able to make predictions, then we can get some lead time before the actual influence on human disease, and that gives us more time to act. We need to keep in mind, however, that there are also a lot of non-climate factors that influence malaria transmission. In terms of parasite movement, parasites tend to be moved by people more than mosquitoes. People travel much longer distances than mosquitoes do. There are other factors like the accessibility and quality of healthcare that determine whether the healthcare system is able to effectively reduce malaria impacts. Also, the timing and the effectiveness of different types of interventions for malaria prevention and control. So we need to keep in mind that although climate's important, it's one of a whole suite of factors that influence malaria transmission. So that's the intro. I'm going to move on and talk more specifically now about some of the remote sensing data sets that we've used to work with malaria in Ethiopia and some of the tools and the processing steps that were involved. And what I'm going to talk about is related to a project called EPIDEMIA. This stands for Epidemic Prognosis Incorporating Disease and Environmental Monitoring for Integrated Assessment, giving us the acronym. So this was computer software. We started working on this when I was at South Dakota State University and have continued at the University of Oklahoma. And initially, we worked with a variety of partners in Ethiopia, the Health Development and Anti-Malaria Association, an NGO, along with the Amhara Public Health Institute and Bahir Dar University. These are all in the Amhara region of Ethiopia. And we use data-driven approaches linking malaria surveillance data to environmental data from NASA satellites. And we also combined a couple of different techniques for outbreak prediction. So those included early warning forecasts, like I showed you earlier, based on tracking weather fluctuations and then making predictions based on those. And then also early detection based on recent malaria observations. I'll show you this a little bit later. With the early detection, it gives us another way to look at the data where we can also potentially detect malaria outbreaks that are not related to climate. So EPIDEMIA has a number of features that made it particularly well suited for malaria early warning and also taking that to scale. So we based it on free and open source software and data. So that included the R language for actually doing the processing and modeling, as well as NASA remote sensing data that we access through Google Earth Engine. The real advantage to the software was that it automated a lot of the time-consuming steps in the forecasting workflow. So those were things like data acquisition, processing, and formatting, fitting predictive models and generating forecasts, and then also generating information-rich reports that our public health partners could actually use. And we set it up in a way that it could be extended to any location and potentially even work with different diseases. One, not really a limitation, but a requirement is it does require some training and experienced analysts to both operate the software and interpret the outputs. And as one would expect from an ARSET training, we used a lot of environmental data collected by NASA Earth observing satellites. This was a key enabling source of data that allowed us to do this work. Why? Global availability, spatially continuous observations. It was frequent enough observations for us to be able to use, and we could also access it rapidly enough within days to be able to actually use it to make forecasts. So the critical data sets were land surface temperature, originally from MODIS, now switching over to VIIRS, and you can kind of see that in the top graphic on the right. That's in the Amhara region, the mountainous region around Lake Tana there on the left, and you can clearly see the temperature gradient from lower to higher elevations as measured by land surface temperature. We also used a variety of vegetation and other spectral indices from MODIS and VIIRS, and then precipitation, starting out with TRIM, and then eventually moving over to the Global Precipitation Measurement Mission iMerge datasets once those came online. So we have to process these in a variety of different ways to translate the raw observations into environmental indices that we can use in our models. So this just summarizes that. In terms of the land surface temperature, we worked with daytime, nighttime, and mean land surface temperature. In terms of the spectral indices, we had everyone's favorite, NDVI. We looked at a few variations on that, soil-adjusted vegetation index and enhanced vegetation index. And then the normalized difference water indices. These are the difference indices that have shortwave infrared and near infrared in them. And we had a couple versions of that. And then finally, total precipitation from the iMerge product. And we pushed these through a series of data processing steps. And there's really nothing in here that's super tricky. This is all basic stuff. Date filtering, application of QA screening to remove bad pixels, calculation of the actual indices that we want, and then doing zonal summaries by Warda. Warda here is actually essentially the spatial unit or district in Ethiopia. It's the spatial resolution at which we have the malaria case data, so we had to connect it to that spatial resolution. And again, none of this is these are all pretty basic operations that you would apply to gridded spatial data. But the challenge is that they need to be done on potentially a lot of data, and they need to be repeated, replicated over and over and over again to be able to make forecasts on a regular basis. And looking at the data, these are some examples of them mapped. So these are mapped across all of Ethiopia. If you look at the maps on the right, there is a lattice of wardas or districts for all of Ethiopia overlaid on the top. And you can see some of the different patterns of precipitation, the various spectral indices, and also land surface temperature. And I would just point out that in order to do this, we developed an app in Google Earth Engine. We called it Retrieving Environmental Analytics for Climate and Health, the REACH application. We actually have a paper out on this. The code is available if anyone's interested. I'll have references at the end of the talk. But basically, this was an application where an analyst could just go online, select a date range very quickly, and then download the data. So the data are all processed in the cloud, and all of the steps that I just showed you in the previous flowchart are carried out in the cloud. And what the analyst gets back and can download is a Warda level table, which you see on the right. So those are the district level summaries that can feed directly into the models. So this is something that would, take potentially just a few minutes a week for an analyst to run and to access the data. So again, this is very critical, particularly in a public health institution where the people using it don't, even if they have the expertise to work with the satellite data, they probably don't have a lot of time to spend on data crunching and summarizing and checking their results. So being able to access a tool like this is critical for allowing us to develop this type of early warning application. So to be able to leverage the Earth observation data, just having them isn't enough. We have to be able to connect them to some type of response data for malaria. And those are weekly surveillance data from Ethiopia's Public Health Emergency Management System. So these are confirmed Warda level counts of malaria cases. And we started out working with 5 years of data from 2014 through 2019. These actually include 2 different types of malaria caused by 2 different parasite species. falciparum and Vivax. And working with these data required multiple levels of processing. So we have to harmonize them with other data sources, particularly the remote sensing data. There is a challenge with screening for suspect values and then imputation of missing and suspect data. So let me talk about some of these challenges because these are specific to the application in Ethiopia. But in my broader experience, these are more general types of challenges that we often have to grapple with, whatever your application is and wherever you're working. So geographic data are not necessarily consistent. We have a variety of issues going on here. One is that the word is these Ethiopian districts are continually being split to deal with population increases. So that's a challenge. We don't have the same malaria data from the same spatial units over time. So generally what we do is we go back in time and aggregate everything to the oldest spatial resolution so that we have a consistent time series. There are spelling challenges. This is Amharic is a scripted language. A common challenge with any language like this is that when you have names, they don't have a direct translation into English. They're translated phonetically. So there tend to be a lot of inconsistencies in the way that things are named. So there's a fair amount of work that typically needs to be done to come up with a consistent geographic data set that we can work with. Another challenge is the malaria data by themselves. So these are actually collected at a network of hundreds of rural health posts and other health facilities distributed throughout Ethiopia. So generally, when someone presents with symptoms of malaria, a rapid diagnostic test is administered. And if that person tests positive for malaria, they're given appropriate drugs and other treatment if necessary. So what happens is these data are collated at the level of these individual health facilities. And then using email or text messages, these get aggregated up through the health system to a district level and to a zone level, to a regional level, and finally to the national level. And this is actually, an amazingly efficient system. And I would say that Ethiopia has probably developed one of the most effective health systems and malaria surveillance systems in Africa. But it's not perfect. You see an example here. There are a lot of reasons why health posts might not be able to report in a certain week. So we end up with these gaps in the data set, and we need to fill them in or correct for them somehow to be able to use the data effectively. So in this case, what we did was we used a robust linear model to basically set a threshold and identify these dips in the data that are suspect, that are not likely to be natural fluctuations in malaria transmission. So we can flag those. And then when we flag them, we actually use the same robust linear model to fill them in. So we have, although there's uncertainty there, we have much more plausible estimates of the actual malaria burden in a given week, because it's not plausible to expect that it's going to drop all the way to zero and then shoot up again in the next week. So this way, we end up with a cleaner and more usable malaria data set. And this is what the data ends up looking like when we've gone through the whole process. So we do the cleaning and the harmonization with the malaria cases and with the geographic data. We use the processes that I showed earlier to process the remote sensing data, summarize it at that WARDA district level, and connect it. And we might see something like this. We see a time series of malaria cases that is, has some patterns in it, but seems quite irregular in some ways. We look at land surface temperature, a satellite moisture index, and precipitation. We see strong seasonality in those as expected, but some variation within each season and from year to year. But it's kind of hard to look at this and try to figure out what the relationships are. They don't jump right out at you. So when we apply time series models, what they generally do is they actually take one of these complex time series and they try to decompose it into predictable components. And rather than get into a lot of the math behind that, I've got a picture here that I think will illustrate that well. So if we look at that time series of malaria cases at the top, we can look at it as essentially a sum, an aggregation of different time series components. There may be a long-term trend in there that reflects long-term climate change or long-term impacts of interventions. There's a seasonal cycle in there that reflects seasonal weather patterns related to precipitation and temperature. And then we can look at the components of the time series that are actually predictable based on anomalies of temperature and moisture and precipitation. And so this is that outbreak signal that we're trying to predict. So, for a given time of the season, in the context of a longer term trend, when are we actually seeing combinations of weather factors that are driving some type of rapid increase or outbreak of malaria? To capture these relationships between climate variation and malaria, we use another common time series method, which is modeling lagged effects. And here's an illustration of what that means. Let's say we're measuring malaria in every week of the year. So the numbers represent week of the year, 29 through 50. And then we also have precipitation that we're summarizing on a weekly basis. We might expect that precipitation is increasing larval habitats, and then that is leading to larger mosquito populations, which is gradually increasing malaria transmission. So it may take some time for precipitation in week of year 35 to influence malaria in week of year 44. The problem is we don't necessarily know exactly what that lag is going to be. Maybe it's really 9 weeks. Maybe it's 11 weeks. And if we start looking more and more, part of the challenge is we've got almost an infinite number of these different lags that we could look at. And that starts to create problems if we want to put a large number of these lagged variables into a single predictive model. We use a technique called distributed lags that allows us to model lagged effect as smooth functions of time. So if you look at the graph, this is an example of a distributed lag. Rather than picking, one single lag length of, say, 10 weeks, what this is showing is that we might have weak precipitation effects at very short lags. At that point, there hasn't been enough time for a precipitation increase to influence mosquitoes and malaria transmission. Then we may see a peak, in this case, between 30 and 80-day lags. So there might be a lag time at which those effects are strongest. And then we see that lagged effect decreasing over time. When we get out to multiple months, then too much time has passed, and other types of weather effects or other factors have superseded that precipitation effect, and we don't see the lag anymore. The main advantage of distributed lags, though, is that we don't need to guess ahead of time what the lag effect is going to be. So this is a machine learning technique because it's actually looking at our data and estimating the timing and the strength of that lagged effect from the data themselves. So it's a huge advantage, and it allows us to estimate these lag temporal effects much more efficiently. One other thing that we need to consider is that we don't necessarily expect lagged effects to be the same everywhere. So different geographic settings, whether it's elevation, hydrology, or human factors, are going to influence how precipitation translates into mosquito habitats, for example. And the best way that we found to handle this is through geographic stratification. So we don't necessarily assume that across the entire country of Ethiopia, or even across a region of Ethiopia like Amhara, that precipitation is going to have the same effect on malaria everywhere. So this is a part of the Amhara region that has dual peak rainfall, and you can see that it has the distributed lag effect peaks at about 70 days and declines thereafter. And then this is a different part of Amhara that has a single rainfall peak, and this actually has a much shorter impact. So the strongest impact on malaria is at lags of 1 to 4 weeks, and then we see a general decrease in effect as a function of increasing lag time. So this allows us to highlight different parts of the region where we get different types of lagged effects. And basically it allows us to develop a family of predictive models, and each of those models is optimized for a particular subregion in Ethiopia. To identify the clusters to use, we have to apply some type of optimization method. For example, we have in the past used a genetic algorithm to try to look at a variety of different clusters and let them evolve to a set of optimal clusters that maximizes the accuracy of our models within each cluster. But there's a variety of different methods that can be used to do this. Let's talk about implementation now. So we've talked about the models a bit. This is stepping back much further and looking at the entire forecasting system and thinking about how it works. And here I have it broken down into 3 components. One is the initial setup component. So a lot of that is data acquisition and processing. I've talked about that some already. And then there's the model selection and clustering. I've talked about that a little bit as well. But these are all things that need to be done beforehand to prep and set up the system for malaria forecasting in a particular area. Once it's set up, the idea is that it's implemented weekly. So this is the same cadence at which the malaria surveillance data is collected. And the idea is that each time a new weekly set of malaria surveillance data comes in, that's added to the database, and a new model prediction is generated. So that involves updating the malaria data and also the remotely sensed data, and then implementing the forecasting models to generate the forecasts and produce maps so that the results can be communicated and used in the public health arena. A third element that we have in there is model evaluation. And this is something that is really important, but often gets lost or maybe gets done once and not done again. If you're going to be doing forecasting, it's actually really important to be able to communicate how accurate your forecasts are. So one of the things that we wanted to do here was to actually build forecasting tools into the model itself, into the system, and automate them to make it easy to validate the forecast. And then ultimately, the idea is through this evaluation, one would eventually come back around after a certain period of time and make some changes and perhaps try to alter the model selection, alter the data that's coming in to try to improve the forecast. So this is kind of the big picture. Here, we're going to zoom in a little bit and look at the weekly forecasts in more detail, because this is really the heart of the implementation, is being able to actually run the system each week, generate the forecast, and get the outputs to decision makers. So the critical steps here are obtaining new epidemiological data. So this would be queried from the Public Health Organization surveillance database. And so the user obtains these data, and then, as I showed earlier, they run the Google Earth Engine script. They download environmental data into a folder, and those data are accessible and ready to go. And then at that point, running the model really just involves getting the data into the correct folders and running a big customized R script. So that invokes some specialized packages that we've developed for model implementation and for doing the clustered modeling, and also does automatic report generation. So as opposed to just a bunch of arcane model output, we're getting the output in terms of interpretable maps and charts. I want to just mention a little bit about our rationale behind the way we designed EPIDEMIA, because we took kind of a middle road. So if you look on the left side, all of these things are things that could be done, manually using R or other software on local workstations. And so this requires minimal costs, can leverage existing computer resources. The problem with doing everything manually is it's time consuming, it's inconsistent, and it's really difficult to replicate. And it tends to really strongly depend on, individuals who are extremely familiar with all of the code and all of the processes. If you look on the right side of the slide, another approach would be to say, okay, we want something that is completely automated, menu-driven, and web-based. So there we automate everything. And, we box it up and we put it on the web or in the cloud and make it so that, with just a few clicks, everything can be run. And that's a great solution. It does have a higher cost for development. I think the other thing with this type of approach is the cost for maintenance tends to be higher than you think, particularly if you have a system that's interfacing with a lot of external data systems. It requires a lot to keep everything up and running all the time. There are issues with, depending on the data source, data sharing limitations, where public health institutions are willing to upload their data, what kind of security protections there are, and then a lot of challenges with the underlying system integration. We went with this middle road, which I would call a semi-automated system running on local workstations. So this is much faster than the manual approach. It's much more consistent. It can be implemented on workstations, laptops, and is very customizable. There are still challenges with like troubleshooting across diverse systems, still some manual steps required, and then putting it all in R and RStudio is a good decision because it makes it very doable, but those are still challenging and intimidated to some users. So that is the rationale between our middle approach for the implementation. And let me show you some of the outputs, because this is, when we look at the actual application, the public health implementation, this is really what it's all about. And we actually worked with our stakeholders quite a bit on this through various workshops to make sure that we were giving them outputs that were useful. And I think one of the key things that we heard back from them is they wanted very information-rich outputs. So they didn't want just a light going on or an alarm going off when there was an epidemic alert. They wanted to see details of maps and charts, and they wanted to be able to look and understand about what's been going on for the past several months, what's actually happening with the environmental variables, because they, as they said, they're the experts. They understand these systems. They know malaria. So they want to see the alerts, but they also want to think about them in the context of the underlying data. And so that's the rationale behind how we design these. So these are summary alert maps. So the idea here is to get a quick regional overview. And you can see we have early detection alerts and early warning alerts. And we have different levels of these. I talked about this a little before. The idea of the early warning on the bottom, those are longer lead forecasts up to several months into the future based on observations of the satellite-based environmental data. Early detection is shorter term. That's actually looking at recent fluctuations in the case data and trying to look for anomalies in the case data that might signal the beginning of an epidemic. So that is with the early detection, we have less lead time, but we have the potential to pick up on other types of epidemics that might not be weather or climate driven. And this is zooming in to one of those districts. This is a time series report or dashboard. And there's a lot packed in here. But the idea is that if you look at the vertical dashed line right in the middle, that's the date of the forecast. So everything on the left side is historical data. We have observed malaria cases. We have previous predictions, so people can eyeball it and get a sense of how well the model has been predicting recently. We have also on the left is early detection alerts. So those are weeks where the observed malaria cases is exceeding an expectation, what's considered the normal number of malaria cases for that particular week of the year. And then when we look over onto the right, those are forecasts. So the dashed lines are the early warning forecasts going into the future. And then when those forecasts are exceeding the outbreak threshold line, we see those triangles or alerts. So, in this case, if you look at the top for Plasmodium falciparum, the model is forecasting an outbreak, an abnormally high incidence of falciparum malaria going out several months into the future. And then if we drop down to the bottom part, these are the satellite observations that are driving the early warning forecast. So we have precipitation, we have temperature, and we have a satellite moisture index. And then we have some envelopes there for the historical distribution, so that someone can look at it and get a sense, okay, so that's the precipitation, but is it wetter than normal or is it warmer than normal? So here we see precipitation anomalies historically that are, in this case, likely contributing to the forecast of a malaria outbreak going into the future. Here, I just want to look in a little bit more closely and highlight that difference between early detection and early warning. So to reiterate, early detection alerts are triggered when the observed value is higher than the threshold. And thresholds are calculated using an algorithm called the Farrington algorithm. It's an epidemiological model that looks at historical case counts and patterns and basically tries to estimate what is normal during a given season, what's expected at this time of year. So if you look on the left, you can see that cases have just shot up in the past couple of weeks. They've broken above that threshold, and that is an indicator that cases are at least somewhat likely to keep climbing into the future. And then going over to the right, again, early warning is looking into the future. So looking at current and recent weather conditions, are there risk factors that suggest that the incidence of malaria is going to be abnormally high in the future? And these are driven by those distributed lag models that I just explained a little while ago. And yes, in this case, you can see that the prediction is that the numbers of future malaria cases are going to be above that threshold level. This is an example of a chart produced by our validation reports. As I mentioned before, this is something that's important, and we built it into the system so that users can get automated assessments of how good the model is actually performing. We use skill scores. This is a common technique used to evaluate weather forecasts. So what we're doing here is we actually compare our prediction to a null model. So what we want to know is, does our model actually do any better than just using, say, the historical weekly average, or using the number of malaria cases from the most recent week and predicting it for next week or out into the future? And if you look at the skill scores, above 0 means that we have skill beyond these naive models. And what we can show fairly consistently across different areas and different models is that we have positive skill out to 12 weeks in the future. So we can demonstrate that these models are actually giving us better information, more accurate forecasts than just simple back of the envelope predictions. Now I want to reflect a little bit on the advantages as well as the challenges of using remote sensing data for this particular application. So there are a lot of benefits to using remote sensing data. First of all, it's freely available. That's huge. It's the consistency of the measurements in time and space is essential for this type of forecasting application. And really, to do what we were aiming for with malaria early warning in Ethiopia, this is really the only feasible source of environmental data that we have. And I can also emphasize that it does provide some fairly critical information about key environmental determinants of malaria, both temperature and precipitation. There are drawbacks, though. The high volume of data processing is a challenge. It's become less so. When I first started working in Ethiopia, most of the internet there was still dial-up. Now, high-speed internet is the norm, but still that burden of managing and processing large volumes of data is something that's a challenge for public health institutions. As with all optical IR data, we have issues with data gaps and anomalies related to clouds. That's something that we have solutions for, basic gap filling methods, but that's still a challenge, particularly during the monsoon season when we get very persistent clouds and rain over much of this region for several months of the year. The other thing is we don't have data on all the key environmental determinants. I would point out, for example, that land surface temperature is not the same thing as air temperature, which is really the most relevant measurement. But when we're looking at fluctuations over time versus trying to get the exact air temperature, it's worked pretty well. There are some other things like humidity, though, where we don't have an optimal satellite measurement that tells us about atmospheric humidity. We can make inferences from recent rain. We can make inferences from greenness and various types of spectral indices. But, the current suite of satellite observations doesn't give us everything we need. These were some of the major barriers to integration and how we address them. So I've talked a bit about the challenge of dealing with large volumes of satellite data. This is mainly a technical challenge, so we were able to address it with technical solutions, development of automated systems, cloud-based implementation. And I feel like we've made a lot of progress in knocking down this barrier. Accessing the malaria data is also a barrier, but for different reasons. I mean, part of it is data quality issues. There are challenges with processing it, but often there are a variety of reasons why public health institutions don't want to give out their data very freely. And this isn't just Ethiopia, this is all over the world. And those are more, administrative, political. So this was part of our motivation for designing the system for local implementation. So rather than saying, hey, you have to give us all your data first, and then we'll make this work for you. We specifically designed the tool so that we could bring it to the users and their data and have them use it in their offices on their systems. And, this doesn't solve all of the problems, and it maybe creates a few other problems of its own, but I feel like this has worked very well. And, again, at least at the beginning, there was a lack of familiarity with the satellite data, uncertainty about whether it was suitable for this particular type of application. And this is the classic thing that we address through training and capacity building, doing this going back 15 years or more. So again, I feel like this is an area where we've made a lot of progress and actually built a lot of knowledge and interest in satellite data and using it for a variety of applications. So long-term sustainability and implementation is always the big challenge. The work we do tends to be project-oriented. We have 3-year projects. If we're lucky, we might get a 5-year project that's long. But long-term sustainability has to be longer than that. We also deal with the fact that in public health agencies, that there are really limited resources for implementing early warning systems. There's a lot of interest, but there's a lot of, there are a lot of things going on, and a lot of the resources are going into responding to other types of emerging challenges. The software needs to be maintained and updated. We've had disruptions to malaria surveillance programs from COVID, from conflict. On the remote sensing side, our satellite missions are not eternal either. We went through the TRIM to GPM transition. It wasn't, it was manageable, but there were challenges that came up. And I think there's something, similar going on now as we look at moving from MODIS to VIIRS and needing to be able to stitch those together if we want to really have long-term continuity. I mean, and these are all things that, we know about in the remote sensing world. People have done research on this. But then when you look at rolling that out in an application, there are new challenges that emerge when we have to figure out how to really pull it off. And then I think overall there's a need for more expertise in Ethiopia, but again, it's not just there, around the world, in terms of satellite remote sensing, epidemiological modeling, software engineering. And to do this, it really requires more than just individual workshops. It really requires long-term efforts to build expertise and develop communities of practice. And I feel like we've seen substantial growth in this over the past 15 years. In Ethiopia, and again, I think more broadly in Africa and around the world, there are more people now who have strong data science skills and are actually quite excited about opportunities to engage in projects like this and make a contribution. I'll say that there are always alternative data sets, and I'm going to offer up a graphic here. This is from a paper that I did with some colleagues a few years ago in Trends in Parasitology. So this is specifically on kind of new frontiers in the application of satellite data for malaria research and applications. But we tried to organize the different sources of data here and how they connect to different components of the malaria system. So if you look across the top, the gray boxes, those are all satellite observations that we can get, often from different sources. And that's everything from, precip, land surface temperature, spectral indices, which I've already talked about. We can do water bodies, soil moisture, land cover, land use, population, individual buildings. Those are all widely accessible now. And then they feed in a variety of different ways. So again, if you look on the left, that orange box, I don't know if it's actually a box with rounded corners, but that's kind of the pathway that I've talked about a lot with my examples in EPIDEMIA. It's really looking at some of these products that are giving us short-term fluctuations in climate and weather that feed in and affect mosquitoes and their parasites. But then, there's also the land cover, land use angle, which is taking a more spatially explicit, higher resolution look. There's also the human side as well, and that's not something that I've talked about as much here, but that's taking land cover land use, population, and building maps and understanding more about the human side versus the mosquito side, and understanding where exposures and vulnerability may be most conducive for malaria transmission. So this kind of a broader outline of more pathways through which we can connect satellite observations to malaria, and showing you how the EPIDEMIA example fits in. And this is just another look here. So this is looking at individual missions, and data products. So MODIS, VIIRS, Landsat, and looking at some of these different themes. So again, that pinkish orangish box, the climate variation theme, that's what I've emphasized in my presentation. And you can see, MODIS, VIIRS, IMERGE, some of the precipitation products. There's a suite of different measurements that are typically at coarser spatial resolutions, but fairly high temporal resolutions, around, roughly daily or shorter, that are optimal for looking at climate variation. When we look at individual landscape features, that would be, individual buildings, individual puddles. That's going to be our very high resolution, 1 to 5 meter resolution data, which would include PlanetScope, as well as a variety of mostly commercial satellite products. And then in between those, we have, Landsat, Sentinel, and a variety of other products that are looking maybe not at, individual buildings or habitat features, but are useful for characterizing land use and habitat types a little bit more broadly, in a way that are relevant both to mosquito habitat, but also to the human element of malaria transmission. And finally, I'm going to offer a few pages of resources here. These are various papers that we've written on malaria early warning, malaria ecology in Ethiopia. Some of them are more research-oriented. Others specifically focus on development and implementation of forecasting tools for public health. But I invite you to look over these. If there's, any of the things that I've talked about where you'd like to take a bit of a deeper dive, and if you have any questions about these, I would be happy to follow up. That is all I have. Thank you very much for your attention. I hope you found it interesting, and I'm going to hand it back over to Asaf to wrap it up right now.
Thank you, Mike, for that excellent presentation. Now, in summary, what have we learned today? First, in Ethiopia, new malaria risks are emerging, which requires accurate forecasting to support rapid, targeted interventions to reduce public health impacts. Two, the epidemic prognosis incorporating disease and environmental monitoring for integrated assessment epidemic system uses satellite remote sensing data, including MODIS land surface temperature, MODIS and VIIRS vegetation greenness and moisture indices, and rainfall from the GPM emerge. The epidemic process involves access and pre-process of remote sensing data on the cloud through the Google Earth Engine platform, gathering recent case data from Ethiopia's public health emergency management system, harmonizing and integrating data, accounting for missing data and changing boundaries, and then running forecasting model to produce a report of early detection and early warnings of malaria. 4, remote sensing data provides the only feasible source of required environmental data in Ethiopia. And lastly, high data volumes, transition to new missions, need for local training on the use of satellite data, and limited resources to sustain long-term implementation are continuing challenges. So to summarize, at our 2-day training session, a number of things we learned over the 2 days is that remote sensing data sets that are commonly used to study climate-sensitive infectious diseases include data from MODIS and VIAS with respect to land surface temperature and vegetation. We also have additional high-resolution data sets from Landsat and Sentinel, which gives us an indication of land use, land cover change, or perennial and ephemeral water bodies. We also have precipitation data coming from GPM Emerge. 2, the common benefits of using remote sensing data include, but are not limited to, being able to have a diversified menu of parameters that are derived from satellite measurements, the broad availability of these data sets, consistent and repeat coverage of the data, and then also free accessibility, especially of NASA data. We also have learned that there are a number of common challenges regarding use of remote sensing data, and this include, but are not limited to, data discovery, quality assessment, gap filling, and large data volumes. So just as a reminder regarding homework and certificates, homework will be posted on the training website and will be due 2 weeks from the time of posting. Answers must be submitted via Google Forms. And regarding certificates of completion, this will be awarded to people who attend live webinars. Attendance is automatically recorded. Completion of homework assignments by the deadline is a requirement. And lastly, you receive a certificate via email approximately 2 months after completion of the course. Here is the contact information for your trainers during this particular 2-day training session. You can find more information about ARSET trainings on the ARSET website. And then you can also follow us on the ARSET YouTube channel. Thank you very much for attending this training. We hope that it has been reaching to you and you can use the knowledge you gathered here in your particular engagements in this area of research and application.
Okay, so thank you everyone for attending our second session of this training. And we hope that it has been reaching for you all and you can follow it up in your projects. We have some questions to summarize this particular session and I'll read through them and Dr. Wimberly will answer as necessary. The first interesting question that I see here is question number 3, and it relates to land surface temperature. And the question is land surface temperature a suitable proxy for air temperature?
That's a great question, Asaf. And, I think the answer is a definite maybe, as is often the case. So I'll just, to answer that, land surface temperature is different from air temperature. So when we think about mosquitoes are surrounded by air, whereas land surface temperature would be the temperature of the uppermost surface of the Earth that's actually being observed by a satellite. So that could be a parking lot or a road or the top of a building or the top of a vegetation canopy. And so the temperature of that surface is not the same as the temperature of the air just above that surface. And I won't get into the physics of that, but it's a different thing that we're measuring. So, for example, if you wanted to get a precise estimate of the air temperature at a given location, a measurement of the land surface temperature at that location is likely to be very inaccurate. However, what we found is that if you're tracking temperature on a daily or a weekly basis at a particular location, and you're looking at what we would call a deviation or an anomaly, so the difference, compared to the long-term average on a particular day at a particular location, is it a hot day or, is the temperature above average or below average? When we look at those anomalies, that variation in the land surface temperature actually tracks air temperature pretty well. If it's a hot day, if the air is hotter than normal, the surfaces are probably going to be hotter than normal, and the other way around as well. So if what we're looking for is relative variation over time, land surface temperature, it's not perfect, but it does a pretty good job and is a reasonable proxy in areas where we don't have air temperature to look at.
Okay, thank you very much, Mike. The second question that is interesting, I think, is question number 6. Does distributed lag effect link the daily value of precipitation prior to the daily malaria measurement, or are there some aggregation precipitation effects over a long time period, weekly or monthly?
Yeah, so distributed lags are a little tricky to wrap your head around, and they're tricky to explain verbally, but I will do my best. So the idea of that 180-day period is that's the maximum time into the past over which we would be looking for a lagged effect. 6 months is kind of long for a lag effect, but we allow it to go back and search over a fairly long lead time. And essentially, what we're looking at with that distributed lag is it's a weighted effect of all of the days going back 180 days. So that doesn't mean that all of those days are having an effect, depending on the way those weights are parameterized. If it's a scenario where we're seeing very short-term effects, then the more recent days would have a higher weight. If it's a longer-term effect, maybe spread out over a couple of months, then we might see, the days over that 2 or 3 month period having similar weights. So, but just to kind of go back and reiterate some of the points that I was trying to make in the presentation, the idea of the distributed lags is that generally it's hard to guess the exact structure and timing of lagged effects beforehand. So really, what the distributed lags are doing at the most basic level is we're kind of searching over that whole 180 days and then trying to see, are there, and usually it's not like an individual day effect. If we look at them over a range of weeks or months, when and where are those effects occurring?
Okay, thank you for that, Mike. And then a set of related questions here that I think should be straightforward to answer. How much does it cost to use EPIDEMIA? And can EPIDEMIA be used with Python instead of R?
So it is, EPIDEMIA is free. The code is on a GitHub page. So yeah, the software is free and open source. The cost is time, because it's free and open source, and because, as I described in that one slide, it's not set up to be a push button application. The cost is it takes some time to work on it. If you're putting, in particular, a new data set into it. Yeah, it takes time, and time is money, right? Because you could be doing something else with your time. So that's the cost. I will say we're just starting a new NASA supported project for various reasons that I won't go into. We worked on this project for more than a decade, and after COVID and some other things, we had a several-year hiatus, but we're just now at the point where we're looping around, and we're going to do essentially a redesign of the entire code base to make it more easy to use and implement. And that leads into question 9. It's all, the code is all written in R. You could call it from a Python script if you wanted to. We may, when we come back around to redo it, we may decide to do, parts of it in Python, maybe have like a wrapper around some of the R code. The reason that we use R is that there are good packages to work with in R to do the modeling, but it could probably be reprogrammed in Python if someone wanted to do that.
Okay, so a related question is number 15. Can the R code in EPIDEMIA be customized for other diseases?
Yes. So there's nothing in the code that would make it work only with malaria data. So the inputs, well, actually, let me back up. So a lot of in principle, none of the models are specific to malaria. They could use, epidemiological data, case counts by week for any disease. The way that the visualization and the reports are set up, those are set up for malaria. So they have, for example, Plasmodium vivax, Plasmodium falciparum, that are specifically reported and labeled in the visualization and in the reports. So yeah, I guess the answer is a qualified yes. It would take some reprogramming, but it would work. I would say we also have, and someone mentioned this in the chat, I think, my group also has a very similar application for West Nile virus forecasting in the US called ARBOMAP that's used by a number of state departments of health. The underlying models are actually very similar. There are enough differences in, well, for a number of reasons that I won't get into, we decided to implement the West Nile virus forecasting as a separate piece of software. But it's an example of how these, a similar approach can be used for a different disease.
Okay, thank you. Now, question number 16, and this relates to the work you did in Ethiopia. So who owns the data in Ethiopia? And does Ethiopia share the weekly model forecast publicly?
So the first one, Ethiopia owns the data. It is Ethiopia's federal system, the data, I believe, is actually owned by the regions, although it is sent to and collected by federal agencies like the Ethiopian Public Health Institute. This has actually informed the way that we've designed these software packages because and you know, this is true not just in Ethiopia but in other countries. It's true in the US. Public health agencies generally are not, for a variety of different reasons, aren't excited about handing their data out to other people to do things with. So our approach with EPIDEMIA and our other similar applications has been to build tools that we can take to the public health agencies. So for example, we've set up data sharing agreements where we can use some of the data for the tool development. But the idea is that we give the tool to the users and they use it on their systems with their data. To my knowledge, I don't think that the agencies we worked with in Ethiopia have shared the forecast publicly. They've used them more for internal decision making. I'll say with ARBAMAP, there have been a couple of states that, like South Dakota, Louisiana, that will, they include forecasts on their, West Nile virus pages. So, in another context with a different application, there has been sharing of the forecast, but, that's a decision from the public health agencies. And in Ethiopia, and I think this is true in other contexts, other places as well, to date their thought has been, we want to, we're interested in these forecasts, but they're not the only thing that we're basing our decisions on. We're integrating them with a lot of other data and information that we have, so that they want to do that internally as opposed to putting them out publicly.
Okay, thank you. Now, question 4 is related to question 15, I think, of question 14. So the person who asked this question is really impressed by your work, and he's asking, can he do this kind of analysis with TB?
That's an interesting question. Certainly one could try it. I have to admit, I am I'm much less knowledgeable about the climatic determinants of TB than I am of malaria and other mosquito-borne diseases. I guess I would say it would be interesting to explore and see. To be honest, in terms of using the environmental predictors, I'm really not sure. Other aspects of the modeling approach, such as the early detection algorithms, are, definitely very generalizable to any other type of, outbreak-prone disease. So they should, there's never any guarantee that it's going to work, but you could certainly try it.
Okay, thank you. And then I think I'll go ahead and answer question number 7. Do we need any specific software to complete the homework? And the answer is no. There are set of questions that you just respond to, so you don't need software. And then question 14 is regarding somebody who is needing advice. And it goes, I would like to ask for your guidance on the best approach to working with a 23 years time series data. Specifically, I'm analyzing leprosy cases in a province in northern Argentina in relation to environmental variables such as NDVI and LST. Given the volume of data, I find it difficult to determine the most appropriate analytical strategy. Any recommendation or guidance would be of great help.
So yeah, that's a big question. The short answer is I'm not sure exactly, but I can offer a few suggestions. So one of the challenges of working with time series data is that it has multiple signals embedded in it. So there is often a strong seasonal component. So you'll have like a repeating cycle every year. There is often a trend component for a variety of reasons, over multiple years and decades, with a long time series like this, you might see, a general increase or decrease, or you might see, some variation from year to year. And then, sometimes we see anomalies. There might be a big outbreak year in 2013 or, 2022 or whenever that stands out from the rest of the time series data set. So, and in my mind, that's one of the big challenges is that when we, attack these data sets with time series methods, we need some way to separate those out. I would just the general suggestion that I would give is start with visualization. There are a variety of time series decomposition methods out there. STL is kind of an old one that's been around for a long time, but there are a number of those. And those allow you to separate that data set out into like the seasonal cyclical portion and a trend portion and maybe an error anomaly portion. And I think that helps to start getting a better sense of what's interesting in the data set that you might want to try to predict. Again, one of the challenges is that what's driving, often the seasonality is being driven by some aspect of the climate, a rainy season, a dry season, a warm season. And so often you can predict that seasonality fairly well with climate variables, and that's an interesting exercise. However, because you have a climate-driven seasonality, it doesn't mean that the same factors are necessarily driving the trend or driving anomalies. So breaking those pieces apart and looking at them separately is often interesting. I guess the only other thing that I would say is, I think it's good to start simple, do some decomposition, do some correlations at different lags, look at your data in a variety of different ways, scatter plots, time series plots. One problem that I often see, and because I teach data analysis, so one problem that I commonly see is people will go immediately to a complex model, either a complex time series model like an ARIMA model, or throw it into some kind of a machine learning or deep learning framework, and you get something out of it, but in terms of understanding why you're getting those results and what the underlying relationships are, it can be kind of inscrutable. So, again, my general recommendation would be look at your data in a bunch of different ways. Start with some basic, simple analyses, and that will hopefully give you, a better understanding of what you're working with and what some of the relationships might be before you take it up another notch to a more sophisticated modeling approach.
Yeah, now a couple of remote sensing related questions. Yeah, so this is question number 17. Which specific spectral features or narrowband indices derived from hyperspectral data are most effective for detecting such changes in vector habitat quality related to changes in water quality, specific host, plant health that are driven by climate variability?
That's a very interesting question. I mean, here the short answer is I don't know. I don't do much at all with hyperspectral. I guess I would say, if you really wanted to leverage hyperspectral data, I feel like it would be most useful, at a much higher spatial resolution, maybe trying to look specifically at water bodies and, like water quality, organic material content, those sorts of, that might be one guess. But, in general, I think the idea of, looking for, much more specific responses with hyperspectral is, very interesting. So host plant health is mentioned in there. So it seems like that would be a really good example if you were looking at a crop pest, for example, where, there might be like a shift in vegetation conditions that would then make it much more susceptible to a pest outbreak. That would be, one good example.
Okay. Next question is question number 20. That's related to remote sensing. Shouldn't all remote sensing data be calibrated before being used in a model?
I'm assuming that, yeah, I'm trying to think of how to interpret this. I guess based on my interpretation of what they're talking about here, not necessarily. We could relate this back to the land surface temperature question. For this sort of statistical model, for example, it might, there could be some additional calibration that could be done that would improve those land surface temperature estimates. And, I do think in general, anything that can improve, either the accuracy or the precision of the satellite observations would be helpful. With the type of statistical modeling that we're doing in EPIDEMIA, it doesn't, so for example, the fact that land surface temperature isn't exactly telling us the air temperature of where the mosquitoes are spending that time, it's okay. We can work with that, because what we're looking for is more of a relative index over time. We want a stream of data that's telling us something about warm periods versus cool periods, wet periods versus dry periods. There are other types of models, though, that would where the absolute value of temperature is important. So there are, for example, mechanistic temperature trait models that would take an estimate of temperature and then translate it into an estimate of vectorial capacity, or R naught. So in that type of an application, it is actually very important to have an estimate of temperature calibrated as closely as possible to, the actual temperature that mosquitoes are experiencing. So I think, to sum it up, it depends on the context and the type of model that's being used.
Okay, thank you very much, Mike. So question 21 relates to your case study in Ethiopia. You mentioned that there were no other suitable weather data, but how about reanalysis data sets? Can you use those?
Yes, I mean, certainly reanalysis data sets can be used. Also, interpolated weather data sets. So for our West Nile virus work, we use we use NLDAS data, for example, which is essentially interpolated weather data that goes into a land data assimilation system. The issue in Ethiopia with the reanalysis data has to do with spatial resolution. So like the global reanalysis data sets that we would, have access to and be able to use in Ethiopia are fairly coarse. I want to say, I guess I'm being recorded. I was going to say, don't quote me on this, but I'm being recorded. So here goes. I mean, I think, probably on the order of like 0.25 degrees. And in a mountainous area where there's a lot of there's definitely relevant physiographic and climate variation at a finer grain than the reanalysis data sets we would have access to. So that was our rationale for going with the satellite Earth observations in Ethiopia. But yeah, I mean, I would say reanalysis data sets are another valid source of data. They have strengths and limitations relative to satellite data. There are certainly a number of papers that I can think of that are out there where they've, that have used reanalysis data. So, yeah, they're definitely potentially usable, but for a variety of reasons, we thought that the satellite observations were a better choice for this application.
Thank you, Mike. Now the other question, which is number 22, it relates more to regarding combining data sets at different spatial resolution and administrative configurations. So when we download climate data, it comes in a grid or raster format. However, health departments conduct actions in administrative areas, municipalities or counties. Is there a model or tool that can be used to aggregate or summarize climate data in these areas?
Sure. So the most straightforward or the simplest way to do that is with zonal statistics. So that's a basic GIS overlay. You overlay your polygon boundaries on the raster, and you take a mean or a median or some summary in that broader area. And in the presentation, I had mentioned our scientific data paper on the REACH tool, which is a Google Earth Engine tool for accessing the satellite data. So that's essentially what that tool does, is in the cloud, it takes all of the raster data, it does the zonal statistics, and then it takes a large volume of the raster data and reduces it to a much smaller table of estimates or measurements, summaries for each administrative unit. I'll point out that there are challenges to doing that. If you look within a Warada, a district in Ethiopia, or a U.S. county, people don't live everywhere in that county. So you can use other approaches if you have some estimation of, where cities are, where people live. You can weight that zonal summary to try to capture conditions where people and disease are a little bit more carefully. But that's the general approach that one could use.
Okay. Another related question to that is question number 10. How is GEE data extraction in your case study different from just downloading CDS data using a bounding box?
I'm not quite sure. Asaf, do you know what CDS refers to in this context?
I don't know what it is. I would think maybe it's data at some kind of administrative level, or if somebody who asked that question is online, can you tell us what CDS is?
I mean, I can give kind of a general, climate data store. I see. I mean, I'm not familiar with the climate data store. I would think it might be somewhat similar. Hang on, let me get my screen back. So I feel like you could, I'm sure you could get the same data through the CDS. With Google Earth Engine, we use Google Earth Engine because it allows you to write a custom script and turn it into an app. So basically, rather than our end users having to, log into a service either through, Copernicus or NASA, and then download data and do analysis with it. Essentially, that was a way for us to package everything up so that they can go to a website, select a range of dates, click a button, they get the summary table on their computer, and it's in the format that feeds right into that feeds directly into EPIDEMIA. So basically, they don't need to do any additional processing themselves besides, selecting a date range and clicking and then, putting it into the appropriate folder and running the software. I'm sure there are other ways to do that, but for us, when we developed it, GEE was really the most straightforward, simplest and most straightforward approach to get this type of app.
Okay, thank you for that answer, Mike. And now the next question, which is number 24, relates to selection of variables for malaria. It says that, is there any guideline on how to select minimum, maximum, or mean temperature and rainfall for malaria?
So what we did, the way that we did that was through a model comparison approach, where we did, we tried out various combinations of variables, compared them with AIC and BIC statistics to try to find the variables that were most, had the best fits and were most consistent across different regions. So, and we did that in a constrained way. So generally, the way we set the models up is that we had 3 types of streams of data. We had temperature, where we use land surface temperature. We had precipitation, which I think was pointed out in another comment, can be summarized in a variety of different ways. And then we had the vegetation or moisture indices, spectral indices, which are basically using observations, indices of either greenness or vegetation moisture, and tracking those over time as another type of proxy for climate variation. That's a very common approach. So we would set up alternative models where we would have one of the, like one temperature variable, one vegetation or spectral index, and one precipitation variable, and then compare those. We don't want to load up multiple like min and max temperature because those are highly correlated. So that's going to create a variety of problems when we do the modeling. But yeah, I did not get into that in the presentation, but essentially there was an earlier step where we did some model comparison and exploration to select the best predictors.
Thank you. Now I think we'll wrap up on the next question. And this actually relates to some material you had provided at the end of your presentation. And this relates to what are limitations of remote sensing when applied to tracking climate-sensitive infectious diseases. I think the audience would like to hear from you again.
Okay, so this is kind of going back to question 1, right?
Yeah.
Okay, we'll go back to the beginning.
Yes.
So yeah, so for a disease that is climate sensitive, one of the big limitations of remote sensing data is simply the limitations of the measurements. We're almost never measuring the exact variable at the exact scale that is really directly relevant to transmission. So and we talked about that already quite a bit in the context of land surface temperature. We also mentioned reanalysis data. So you can get estimates of air temperature that are pretty good, but those are at a much coarser spatial resolution. Even if we somehow could get estimates of, interpolated air temperature at, maybe 1 or, a few kilometer grid cell size, which you can get in some places. The problem there is that those are data from weather stations, and mosquitoes don't hang out by the weather station. They spend, for malaria vectors, they spend most of their life cycle usually inside someone's house, sitting on the wall, which is a different microclimate. So, that is a fundamental challenge that we grapple with, is that we never have the perfect observations. And then there are the factors that Tatiana pointed out on Tuesday, the fact that we have data gaps that we have to fill, for example. So those are all challenges. There's usually not a perfect data source. And, we have to grapple with those data technical issues as best we can. I would add that another fundamental challenge is that there are many climate sensitive diseases. There are few diseases that are only sensitive to climate. So we have to think about the fact that, we may see outbreaks for other reasons besides climate anomalies. And if we're only using climate variables, we're not going to predict them. I'll reference Tatiana's presentation again, where she showed a much broader variety of applications, using remote sensing to map human populations and, things like land use, vulnerability, exposure. So, that's another area that we can get into. In the applications that I've developed, usually what we've done is tried to include something in there that would help us to capture outbreaks that are maybe not clearly triggered by climate. So for example, with the malaria forecasting, we've done that by including an early detection, an outbreak detection algorithm, along with the climate-driven forecast. So the idea being that if we get, sometimes you might get an influx of people bringing in parasites to a certain area that can spin up transmission, even if we haven't had a weather anomaly. And, we can see that and potentially detect it early on with an early detection algorithm. In the US, I'll allude to ArboMap, our West Nile forecasting work. There, what we do is we combine weather data with mosquito surveillance data. So we have another stream of information which comes from trapping and testing of mosquitoes. So we can see infection rates in the mosquito population, and that's another predictor of human disease that has its strengths and limitations. But what we found is that that's very complementary with the climate data. So, whenever we can bring in additional variables, additional sources of information besides only climate to help improve our predictions, that's very helpful.
Okay, now we'll wrap up there, but I want to address a question that somebody has asked about the assignment. The homework is accessible on the training webpage, and it has to be submitted via Google Forms. So I hope whoever asked that question has an answer to that. And then lastly, I would say that if we can use the reaction icon to congratulate Mike for giving the presentation today.
Yeah, and thank you for attending. There are a lot of good feedback and interesting kind of side conversations in the chat. I really appreciate that. There were a variety of other, comments and feedback that I thought was very thoughtful and helpful. So, thanks to all of you for participating.
Yeah, now there are a number of questions probably we didn't answer, and we are going to look at those in detail with Mike, and we'll answer them and place them on the website.
Yep.
The last thing I would say is that please follow us on the YouTube channel. Also check our ARSET training website. We have a lot of interesting trainings. As you may realize, as an organization, we work in many areas, so most of our trainings are cross-cutting, and they can benefit many areas. So please follow us on the YouTube channel to be able to find out what we are coming up with next. And then lastly, I hope that this gave you an opportunity to connect with other practitioners, with other students in many parts of the world, in many regions, and that through that you can be able to build community. And then I would just want to plug, we have this organization called GeoHealth that brings together people who are working in the public health area or disease area. You can join that and be able to also expand your network. Okay, thank you very much. Happy early Friday and have a good weekend.
Take care.